Today's IoT applications are capable of more than ever imaginable in recent years. With these new capabilities comes a need for more power, and thus longer-lasting batteries. Hello, my name is Matt Vaness with Semiconductor, and today I'll be explaining how to achieve a 10-year battery life in medical, surveillance, and agricultural IoT applications. From wearables to remote sensing, many emerging areas within IoT wouldn't be possible without the ease and flexibility provided by battery power. Although offering many benefits over wired and wall-powered solutions, an obvious downside is that all batteries will need to be replaced at some point in time. To limit this inconvenience, many manufacturers aim to provide a battery life of 10 years. Some are even exploring ways of taking their devices entirely off the grid with alternative energy sources such as solar or kinetic energy. There are two methods we're going to look at for increasing battery life. The first is by leveraging the dual-mode nature of IoT nodes. In active mode, IoT nodes have high power draw tasks, RF communication, and high power sensing. In low power mode, the node system remains in idle mode most of the time and waits for a pre-scheduled or triggered wake-up to conserve power and extend battery life. The second method is to employ a deep duty cycle technique. This will minimize time in active mode and extend low power mode as much as possible. Duty cycles utilizing this technique typically are less than 0.001% for nodes with few transmissions per day. Now we'll look at improving battery efficiency with a low IQ LDO regulator for low active duty cycle use cases. As you can see on the chart here, with a load held at a constant 2 microamps in low power mode, a low IQ buck regulator with an IQ of 2 microamps leads to a 7-year battery life. Moving to LDO regulators, an LDO regulator with an IQ of 500 nanoamps leads to a 10-year battery life, while an ultra-low IQ LDO regulator with an IQ of 50 nanoamps offers significantly better battery life of over 12 years. The low IQ LDO regulator we're showing here is the NCP171, which we'll now dive deeper into the measurements of. The table above illustrates the power draw from the battery in two modes of operation, active, in yellow, and low power in blue, as well as the combined average power draw. In active mode, the buck is clearly more efficient due to its higher efficiency of 94% versus the LDOs at almost half the energy draw from the battery. But this is only for a total of 4 seconds per day, or 0.00046% duty cycle. In low power mode, however, for a 2 microamp load, the contribution from quiescent current can become a significant part of the total draw on the battery, depending of its magnitude. A 50 nanoamp of IQ with the NCP171, as an example, is a small increase on the total battery load of 2 microamps versus a 2 microamp of IQ from the buck, which practically doubles the net load on the battery. This combines with a significantly longer time the system stays in low power mode, 86,396 seconds in this case compared to just 4 seconds in active mode, shifts the net efficiency in favor of an ultra-low IQ LDO, such as the NCP171, for extending the battery life or reducing the size of the battery and lowering cost. This chart shows measured average currents compared to the NCP171 with 50 nanoamps IQ against a low IQ buck converter with 360 nanoamps of IQ for varying duty cycles. The use case here requires 2 milliamps of load in active mode and 10 microamps in low power mode. As can be seen, both the average currents and total input power decrease as the total time in low power mode is increased, which is also to say as the active mode duty cycle is reduced. This further proves the math shown in the previous slide and how an ultra-low IQ LDO can outperform a low IQ buck regulator in extending the battery life. The NCP171 is an LDO regulator which is designed specifically for low-duty cycling IoT applications, including wearables. With an innovative dual-mode architecture, the NCP171 provides ultra-low quiescent current when the application is inactive, low power mode, and reliable data transmissions and superior noise performance when active. The two LDO modes can be selected by switching a dedicated eco pin. In active mode, the NCP171 provides up to 80 microamps of load current with exceptional noise and dynamic performance required for reliable RF transmissions and very low noise performance for precision sensing. While in low power mode, The NCP171 draws extremely low quiescent current at just 50 nanoamps for up to 5 microamps of load, leading to significantly increased battery life. To even further reduce power consumption, the NCP171 also offers a built-in voltage offset when switched to lower power mode from 50 mV up to 200 mV. The NCP171 also has a lower overall cost than typical buck regulator solutions due to a smaller footprint with fewer external components. This graph shows use of 2 LDO cores in the NCP171, each optimized for each of the 2 operation modes. The eco pin switches the operation from one mode to the other by enabling the corresponding LDO core. A significant reduction in quiescent current from microamp levels, 52 microamps here, down to close to 50 nanoamps is made possible by toggling the eco pin from high to low, which is disabling the active mode LDO core. The transition time between the 2 modes is fast and in the order of 100 microseconds typically. The eco pin can be driven high or low via a GPIO pin from the microcontroller to switch between active and low power modes. This chart illustrates the wide input voltage range 1.7 volts to 5.5 volts of the NCP171. The wide input range offers flexibility in the choice of batteries, which can be used covering a wide range of options from alkaline, coin cell, and lithium polymer as an example, depending on the cost and space limitations. The NCP171 is offered with a built-in auto startup feature. The auto startup feature ensures the NCP171 powers up in active mode for a set period of time regardless of the state of the eco pin, even if set to low power mode. This feature is to ensure the system can sustain high loads that may be required for any necessary system configuration setting, housekeeping at first battery attach. Another power-saving feature embedded in the NCP171 is the built-in output voltage offset when switching from active to low power modes via the eco pin. The lower voltage in low power mode can further reduce system power voltage by as much as 20% depending on the voltages used. Factory programmed offsets of 50 mV to 200 mV are available at 50 mV increments. The NCP171 is offered in space-saving 1.2 by 1.2 mm XDFN package at a wide range of output voltages and active to low power mode voltage offsets. To learn more about the NCP171, as well as ON Semiconductor's comprehensive solutions for the IoT, including the industry's lowest power, wireless, and complete node-to-cloud development platforms, visit onsemi.com. Thank you.